Hello everyone, greetings of the day. So today we'll discuss about verification of Kirchhoff's current law and Kirchhoff's voltage law for a DC circuit. The videos is presented by Dr. Jagdish, Associate Professor, EEE Department, GSSS IITW, Mysore. First, let us know the background of the Kirchhoff. So he is actually uh, a German physician. He is mainly established the area of spectrum analysis, and Kirchhoff is formulated his circuit laws basically to simplify the electrical analysis. So electrical analysis, which includes to find the current and voltage at various branches of the circuit, and this law basically deals with the current and the voltage in the electrical circuit. Coming to the statements, so Kirchhoff's law is majorly classified into two types. One is Kirchhoff's current law and Kirchhoff's voltage law. So he has stated his law in two different forms. The Kirchhoff's current law says the sum of current entering to the junction point will be equal to the sum of current which is leaving the junction point, or else we can say the algebraic sum of all the current at a junction point is always 0. In the other law, he stated that the sum of potential drop across various elements in a closed loop is always 0. That means the sum of potential rise will be equal to the potential drop. So where E is represented here is electromotive force. These are the two statements and the mathematical representation of Kirchhoff law. So the main purpose of this experiment to conduct here to find out the or to understand the Kirchhoff's laws, that is Kirchhoff's voltage law and Kirchhoff's current law practically by conducting the experiment, and to verify the measured values with the theoretical values. And this law basically it is accurate for DC circuit. That is why we will be conducting the experiment for DC circuits. And when you want to verify this with respect to AC, so it will be suitable for the higher wavelength. Okay, so the wavelength is more, then we can also apply this experiment for the AC supply also. The main aim of this experiment to verify the Kirchhoff's laws, that is Kirchhoff's current and voltage law. Coming to the objectives, so this is to apply for given electrical circuit, and second objective is to determine the various branch current in the circuit, and also to find the voltage or potential difference around each loop. So this is actually basic objectives of the circuit or objective of the experiment. Basically, Kirchhoff's law it is used mainly. So as I told you already, to find the various branch current and the voltage across the element. This analysis makes simple for the calculation purpose when you compare with the series parallel simplification method, whereas in case of series parallel simplification method, as the number of elements and the voltage sources are increased, the complexity of the network will be more. The simplification will be difficult. In order to avoid this, the Kirchhoff's law plays a very important role for simplification of the complex network where it is having more number of elements with the more number of old sources. Okay. In order to conduct the experiment, these are the operators which are required basically. The first one is the regulated supply in order to apply the rated voltage to the circuit. Okay, so in our laboratory we are using which is in the range of 0 to 30 volts, and basically we need two quantities. One is for KVL conduction, another one is for KCL. Okay, so if you are doing at a time, it needs two quantity, or else one regulated power supply is sufficient for the conduction of experiment. And the number of ammeter from 0 to 10 amperes, it needs 4 numbers. Multimeter in order to check the potential drop across the various resistive element, and a decayed resistance box basically to set the different values of the resistance, and of course the connecting wires to rig up the circuit. So this is actually the regulated power supply. Okay, and this is a ammeter, DC ammeter. It is having two different ranges, 3 amperes and the 6 amperes. And this is a multimeter, okay, which is used for the various measurement of various electrical parameter. Whereas this is a decayed resistance box. You can see here in the decayed resistance box, we will be having the two connecting terminal. Okay, and I think the resistance will not have a polarity. We can connect it to the any two terminal, and we'll be having a different knobs here. Each knob will be representing different values. Okay, anyway, these things I will tell you while explaining the circuit diagram for the time being. So this is actually the decayed resistance box. Basically this will be used for the to set the different values of the resistance. Okay, this is actually, well, coming to the Kirchhoff's current law. So we have just simple circuit we are considered here. So with the one voltage source, we have three different resistance, and also we have shown the resistance values to be set for the conduction of the experiment here in the second circuit diagram. And basically this the arrow mark represents the variation. Okay, it is a regulated power supply. We can vary the voltage according to the requirement, and we'll be using the three digital ammeter, okay, to measure the current at different branches. Now first we'll see the theoretical calculations of, then we'll move on to the conduction of experiment, as you already know. Okay, so this is a circuit diagram we are considered. So here we'll be having two different loops. This is loop 1 and this is loop 2. By applying Kirchhoff's law, we can find the current in various branches. As you already know, the resistance value what we have taken here is, it is, you can see the resistance 1 value is 50 ohms, right? And the second one is 100 ohms, and the R3 is 150. So based on that, we'll just do the theoretical calculation first. Okay, as you know, this is the 50 ohm resistor, and this is 100 ohm resistor we can set, and this is 150 ohms, and we'll take the variable supply, we'll apply the 10 volts DC initially. And for this, if you try to do the calculations, okay, so applying Kirchhoff's law for the loop 1 and 2. So here we have a two loops. You will get two equations with two unknowns. So let us say this is I1, and I'll say this is I2 current, and this is I1 minus I2, that is called as I3 current, which is flowing through the R3 resistance. If you apply the Kirchhoff's law, so as I said, there are two loops. We get the two unknown equations, and the first one is, okay, you can take it, you can start from this point. So whenever there is a resistance, there is a voltage drop. So I just say minus sign, so negative sign, minus 50 ohms, the resistance I into R. Actually, the voltage drop here is, I can say it is I into R. Okay, so I here is actually I1, okay, and the resistance value is 50. So this will become minus 50 I1. Similarly, the current flowing through this second one is I2, and it is negative, okay, because both are in the same direction. So minus 100 into I2 current is flowing, and when it is moving from minus to plus, it is plus 10 volts we are applying, that is equal to 0. If you simplify this, you will get 50 I1 plus 100 I2 is equal to 10. So we can call this as equation 1. Similarly, if you apply the KVL for the second loop, so you get the equation 150 I1 minus 149 I2 is equal to 0. I'll call this as equation 2. And by solving equation 1 and 2, so we'll get current I1 as 0.068, solving it by equation 1 and 2, and I2 is 0.066 amperes, and I3 is 0.002 amperes. Okay, so this is I1, I2, and I3. Apply the Kirchhoff law for this. Okay, so these values you can update in the tabular column, theoretical calculations. Okay, as it's already given in the manual. Okay, yes, I think it's visible to you. So here we can update. We have taken it is 10 volts, right? And the theoretical calculation I1, what we got is it is 0.068 amperes. Okay, I1, and I2 is 0.066 amperes, and I3 is 0.002 amperes. Okay, if you take this one, I1 is equal to, I1 is how much? We got 0.066. Yeah, as you can assume, if you add I2 plus I3, that will be equal to 9. That is what actually we need to verify here, and we are getting those value. Okay, and uh, that we will be verifying practically. Once you get the practical, once you take the practical readings, that we are going to verify here with the theoretical calculations. This is about the Kirchhoff's current law. Similarly, to go for Kirchhoff voltage law, okay. So here we have a three different resistors are connected in series, okay, and we need to apply the Kirchhoff's voltage law for this circuit, and will be verify the theoretical as well as the practical readings. So here, as you know, we'll be having only one loop. By applying the Kirchhoff's voltage law, okay, we can find out the current flowing through the circuit first. Okay, then we can find out the voltage drop across each resistance. So here, so I can write that, so all are only one loop, and the current flowing through, I'll consider it as a I. Okay, so and we know the resistance values also, it is known. So we can directly go ahead with the equation. Sum of the voltage drop is equal to sum of voltage rise, that is equal to 0. So this will become 50 in the first, I into R, it is 50 into I minus, because it is a resistance opposes negative, because the direction of current and the circuit diagram current both are in the same direction, so will be considered as a negative minus sign. So minus 30 into I minus 100 into I. When you're going from minus to plus, it is plus. So we'll be applying the 10 volts in the beginning first. We'll say it is there. That is, summation of the voltage drop, okay, and EMF will be always equal to 0. That is actually the Kirchhoff's voltage law. You just simplify this because all are negative, okay, voltage drop. So this will become minus 180 is equal to minus 10. So both, so negative sign can be ignored, okay, 180i. So I will become 10 divided by 180. So we get the value of current as, okay, if you do the calculations, I value will be 0.055. 0.055 amperes. And once you know the this current voltage drop, easily you can find out. It is V1 is equal to I into R1, V2 is equal to I into R2, and V3 is equal to I into R3. Okay. So I is calculated here. So you can directly find out the voltage. V1 is equal to I is how much? 0.055 into R is 50 ohms. So you'll get the resistance V1 voltage drop across the 50 ohm resistor is 2.75 volts. 2.75 volts. Similarly, voltage across 30 ohm is 0.055 into 30, that is equal to 1.65 volts. Voltage across 100 ohm resistor 0.055 into 100, it is 5.5 volts. If you add, okay, all the three values 1, 2 and the 3, you should get the actual voltage what we are applying. So if you add all the three, you get 9.9 volts. What we are applying is 10 volts. If you just verify this, voltage drop is 9.9 and both are equal. That is, we can verify the values. The same thing you can update in the theoretical calculations before going to the practical conduction of the experiment. In the this one, theoretical calculations, V1 is, as we are calculated here, it is the value of V1 is for 10 volts source, it is 2.75 volts, and across V2 is 1.65 volts, and V3 is 5.5 volts, and addition of all these things, theoretical value is 9.9. Okay. Similarly, we can do the calculation for 15 volts, 20, 25 and 30 volts. Okay. So this is about the verification of Kirchhoff's laws. Okay. The same thing, now we'll conduct the experiment and we'll verify the values. Thank you. Now we'll move on to the practical conduction of the experiment. So greetings of the day. So we'll now see the practical conduction of KCL now. So these are the components we are using. This is regulated power supply, and these are the decayed resistance box. So we are using 3 decayed resistance box. Okay, the first one is, anyway, I'll tell you the settings. So for R1, R2 and R3, and for each, so this is the ammeter which is measuring the main current. Okay, then the branch current will be measured by using these 2 ammeters. Okay, and make sure that we are applying DC supply. I'll be considering the DC ammeter with a proper range. Okay, now we'll come to the rig of the circuit, and you can see here we have a DC power supply, regulated power supply for 0 to 30 is a variable one. The positive end of the regulated power supply is connected to the positive of the ammeter. You can see this two are indicating, this is red is indicating positive polarity and the black is negative polarity. Make sure that when you are doing with respect to DC power supply, polarity is very important. Okay, positive polarity is connected to the ammeter, positive. Okay, and negative of the ammeter is connected to the R1 50 ohm resistance. Okay, I'll tell you how to set the resistance value later. For the time being, okay, negative of this ammeter is connected to the one end of the decayed resistance box. Okay, here we have different options to set the resistance, but when you are connecting to the resistance, so there is no need of verifying the polarity. So either you can connect it to any one of the terminals. So negative of the ammeter is connected to the one end of the decayed resistance box. Okay, and another end is connected to two parallelly. It is connected to R2 as well as from the to the R3. Right. So now you can see the another end of the decayed resistance box is connected. One end is connected to the second R2 and other one is connected to the R3. Okay. Next. So another end of R2 is connected to positive of the ammeter. Okay. So another end of the R2 is connected to the positive of the ammeter and negative of the ammeter, okay, is connected to the another ammeter negative. Okay. You can see the negative of this ammeter and the next ammeter negative is shorted. Okay. And when coming to this one, resistance R3 is connected to the another A3 ammeter positive. Okay, and negative is shorted anyway. I already shown this, and this one is negative of this is connected to the positive of the ammeter, and negative of this ammeter and this ammeter is shorted, and from the same it is coming back to the negative of the regulated power supply. You can see here that same thing. This negative terminal and the negative terminal is shorted, and from the same terminal it is connected to the negative of the regulated power supply. So this is about the circuit rig up, and if you see, let us set the decayed resistance box, okay, values here. So actually the same decayed resistance box here, you can see we have a 5 knobs, knob 1, 2, 3, 4 and 5, and the first knob is, it is a multiplication of 1, okay, and second knob is, it is a multiplication of 10. Third knob is multiplication of 100, fourth is 1000 and 10,000. Okay. So now I'll show you how to set the resistance in the decayed resistance box, DRB. Suppose whatever the knob we are turning here, that will be multiplied by 1. So for this case, I'll set the value of resistance is 5 ohms. Okay. 1, 2, 3, 4, 5. So now it is 5 into 1 ohm. It is 5 ohms. Okay, now if you can see, I'll connect this multimeter terminal. You can also see the readings. Right? So it is in the mega. So we'll change the range. It is 5 ohms. Now I'll just change the values here. Now you'll see how to measure the resistance value before making the connections here. Okay. So now you can set the values based on the circuit parameters here. Okay. As I said, so we have a different knobs here. So first we'll see, I'll set the, okay, all are in 0 now, almost the 0 ohms. If I set this to the 5, so 5 into 1, it will become 5 ohms. Okay. Instead of that, we'll go with the second one. So here you can see, if it is 1 into 10, 1 ohms. I'll just make it 1 turn here. See, you can see now the way it is varying. Okay. Additionally, some resistance is included, so it is showing 14 ohms. Now I'll just increase this. This will become 2 into 10, 20. So it is showing the reading. 3 into 10, 30. 4 into 10, 40. 5 into 10, 50 ohms. Correct. Similarly, if you go to the next knob,
it is multiplication of 100. So now it is 50. Now it is, if I change this to 1, okay, 1 into 100, 100 plus 50. So 150 ohms. Similarly, if you go for this one, okay, it is 1000. Similarly, if I change this, it will become 200. 200, 2 into 100, 200 plus 50, it is 250, and 300 into 50, 350, and so on. So like that, you can set the different values. If I go with the K, so 1K plus 350. So 1000, 350. So 1.3 it is showing you. 1.3 kilo ohm. 1 plus 0.3. 1.3 or 1.5 kilo ohms. This is how you need to check the, first you can set the resistance value depending upon the circuit parameters here. You can see now it is 350. If I reduce 250 and it is 150. Now if I reducing this, okay, all are 0. 100 to 0. This is how you need to set the resistance here. Now we will set the resistance value, okay, according to the circuit parameters. Now you can see R1 is 50 ohms. Okay. Now this knob I am going to vary now. Okay, it is into 50. Okay, into 10. So I'll make it, this is 5 into 50. It is 50 ohms. So 1, 2, 3, 4 and 5. So 5 into 10. This now resistance value is 50 ohms. Similarly, R2 is 100 ohm. Okay. What I'll do? So instead of changing these two, I'll just changing this. Okay. 1 into 100, it will become 100 ohms. I'll make it this 1 now. So now it is 1 into 100 is 100 ohms. Similarly, the third value is, it is 150. Okay. In order to do that, so I'll make it, this is 1. So 1 into 100, 100 ohm resistance. And now I'll set this to the 50. 1, 2, 3, 4, 5. 5 into 10 is 50. So add these two, 100 plus 50, it is 150 ohm. So now we have set the different resistance values 50, 100 and 150. Right? Now this is the current which is measuring I1. This ammeter is measuring the main current I1, and this resistance 100 ohm resistor is connected here. Okay, you can see this is measuring I2. I2 is measuring by this ammeter, and similarly this is R3. This is the current what is measuring is I3. Okay, so I1, I2 and I3 will be measuring different currents at a different branch. Now I'll just turn on this regulated power supply and will set the voltage say for 10 volts. We'll be calculating here, or will be noting the values for different values. Okay, different applied voltage from 10 to 30. We'll start from 10 volts now. I'll just turn on this. Here we have two options. One is to set the voltage, coarse knob is there. Another one is fine tuning. Okay, the major voltage can be applied by using this knob. Okay, so now it is 1 volts, 2. Okay, so like this you can set the major part, you can set by this, and fine tuning can be done with this knob. In order to set the exact values. Okay, almost 10 volts. I apply the 10 volts here. Okay, now we'll see what is the current, because the theoretical calculations we are already done with it. We'll just verify this theoretical calculations with the practical values. Now you can see the current is, the main current 0.08. Okay, 0.08. This is the current I1. Similarly, the current I2 is 0.05, right? 0.05 amperes, and current I3 is 0.03. Okay, 0.03 amperes. Okay, the total current here is practical value is 0.08 amperes. So this is for one set of values. We are verifying the theoretical calculations what we did before, and now we are practically checking these values. Okay, there is minute difference here. This is maybe due to the variation of the voltage. Okay, and maybe some of the additional resistance will be included. Because of this, there is very small minute difference is there that you can ignore here. Okay, and now I'll set the voltage to the 15 volts. Okay, and we'll see the reading. Now I'll set the voltage for 15 volts. We'll take the readings. This is a fine tuning. We'll be using this one. Fine tuning knob will be used. 15 volts. Okay, and the current I1 is 0.13 amperes. 13 amperes. Similarly, the current I2, we are not changing any of the resistance, make note of that, and I2 is 0.08 amperes. Similarly, I3 is 0.052 amperes, and the practical value also you can write 0.13 amperes. So this is the practical values for the voltage, set voltage of 15 volts. Similarly, we'll do it for 20 volts. I'll set the voltage for 20. Okay, now the voltage is 20 volts, and can you see what is the current now? It is increases to 0.17 to 18. So I'll take it 0.18 amperes. And what's the value of I2? 0.11 amperes. You can observe this is I2, and I3 is 0.070 amperes. Similarly, the total value is 0.18 amperes. Now I'll increase the voltage again to 25 volts. Okay, I'll just increase the voltage to the 25. Okay, so now the voltage is set for 25 volts. Now you can see what is the current. It is again increases because of the increase in the voltage. It is 0.22 amperes I1. Similarly, I2 here is 0.13 amperes, and I3 is 0.87 or 88, 0.088 amperes, and the total current is same as that I1. It is 0.22 amperes. Now we'll go with the final value for 30 volts, because this is the maximum voltage range is 0 to 30. We can apply up to 30. So now you can see we will apply the voltage of 30, because the maximum value voltage what you can apply from this unit is 30, because it is the vary from 0 to 30 volts. So we are applied the 30. Now you can see the reading. I1 is having 0.26 amperes, and I2 is 0.16 amperes, whereas I3 is 0.108 amperes or 107. So thing you can note down here, and here I1 is same as this one, total current. So this is how we are drawn the practical values. For the same values, you can change the whatever the theoretical calculations we have shown. Similar to that, you just change the voltage value for 15, 20 and 25, 30. Okay, so you can do the theoretical calculations for these values, and you can verify that with the practical calculations. Okay, and finally you should write the result. Okay, the That we will discuss later, the final results and other parameters. So this is about the Kirchhoff's current law, conduction of experiment. Thank you. Hello. So now we'll see how to conduct the experiment of Kirchhoff's voltage law. And in order to do that, so we need, as you know, one regulated power supply to vary the voltage from 0 to 30, okay, and ammeter to measure the current, and 3 resistors which are connected in series. So how we can identify this connection is in series means you can see if there is a end-to-end connection, okay. So one end of the resistor is connected to next starting of the next resistance, and next another resistance end will be connected to the starting of the next resistance, and this will form a series connection. Whereas in parallel, you know, all the terminals will be connected to the common points. Now, so we'll see the regulated power supply positive is connected to the ammeter. By default, we have a here ammeter that itself is sufficient for us, okay. So we'll be using this ammeter to measure the current, and we have a 3 resistance here. They are connected in series. This is R1, R2 and R3 decade resistance box. And you know, series connection, the positive end is directly connected to the resistance 1, and another end of the resistance connected to the next resistor, and next resistance is connected to the third resistance, and finally the end terminal of resistance 3 will be connected back to the negative of the supply. That is what here the circuit diagram. From the positive it is connected to R1, another end of the R1, R2, another end of R2 to R3, and R3 end will be connected back to the regulated power supply negative. And now, in order to measure this across resistance across the or voltage across the each resistance, so we'll be, instead of using 3 voltmeter, so we can use the multimeter, and in the multimeter we can measure the voltage drop, okay. So as you know already, the resistance value here you need to set, okay. So before conducting the experiment, we need to set the resistance value, and as you know, this is 50 ohm, R1 is 50, R2 is 30, and R3 is 100 ohm, okay. I think I have already explained in the previous experiment that you can set the resistance. This is into 10, okay. So I'll make it 5 digit here, 1, 2, 3, 4 and 5, okay. I'll do it again. 1, 2, 3, 4, 5. 5 into 10 is 50 ohm resistance. This is for R1. Similarly, R2 is 30. Okay. So same thing I'll be setting here with the third knob. So 1, 2, 3. 3 into 10 is 30 ohm resistance. Similarly, third one we'll go ahead with this one. Into 100 is there. So I'll make it, this is 1. 1 into 100 is 100 ohms. So now the resistance of the decade box is set now. This is for 50, 30 and 100 ohms. Okay. Now we'll just follow the procedure, okay, and we'll just turn on the supply, apply the different voltages. Okay. You can see here we already calculated the theoretical calculations we already did for 10 volts applied, okay, voltage. And now we'll apply the 10 volts here and see what is the practical values you'll get across the R1. Okay, across R1 it is a voltage V1, across R2 it is a voltage V2, and across R3 it is voltage V3. And finally, in the series, as you know, the voltage will get divided. So V1 plus V2 plus V3 will give the supply voltage. So that we will do it now. Okay. So now I have set the resistance. Now we'll apply the voltage. I'll just turn on the regulated power supply and we'll apply the 10 volts. Okay. See, this is actually the voltage now indicator in voltage meter, and this is a ammeter. Okay. So we can directly measure the ammeter from the regulated power supply itself. So now I'll apply the voltage of 10 volts. As you already know, same the regulated power supply were used for Kirchhoff's current law. I'll just use this coarse knob in order to increase the voltage. Okay, and the fine tune will be used in order to set the exact value. Now it is exactly 10 volts. I'm just applying, and we'll see what is the voltage across this each resistance. In order to set the voltage, you should know it. Okay, we are applying the DC voltage. Okay, this is actually AC symbol, DC symbol, and whenever if you want to measure the resistance, will be use the resistance stuff. So all the parameters will be measured here. Okay, so when you are measuring the voltage and the resistance, it will be in the voltage knob. When you are measuring the current, you should change this to the current knob. Okay, so now we are measuring the DC voltage. I'll set the knob to this DC voltage measurement. See, the knob is set it for DC. You can see here display is also shown the voltage with the, it is measuring the DC. Now let us set it for DC voltage. Now I'll just see. Okay, so what is the voltage drop across each resistance? Okay, we'll measure the voltage. I'll just connect across this knob. Okay, and you can see the voltage drop across R1 is approximately 2 point, yeah, 1 second. It's approximately 2.82. Okay, so I'll write the V1 is 2.82 volt, and practically what we have calculated is approximately 2.75 volts. Similarly, we'll measure the voltage drop across R2. What's the voltage you're getting here? See, it is approximately 1.68. So we'll write that value 1.68 volts. Similarly, we'll connect the multimeter across the third decade resistance box. See, it is approximately 5.59 volts, or I can say 5.59 volts. Okay, so if you add these three, so you'll get approximately 10 volts or 9.8 volts. You just add practical voltage V1, V2 and V3. You can write it here, the total voltage. Okay, similarly, now I'll just increase the voltage from 10 to 15 volts. Right? Now it is exactly 15 volts. If you want, you can note down the current here, but it's not required for the Kirchhoff's voltage law, because we are mainly interested in the voltage drop across the element. Now, so if I connected that, just see what is the voltage drop for when you apply the 15 volts. So it is approximately 4.2 volts. So I'll just write down that value here. For 15 volts, it is 4.24 volts, and for R2, yes, just connect this multimeter terminal across R2. It is approximately 2.5, right? 2.53 volts. I'll write it here for the practical value, 2.53. And similarly, we'll measure the voltage across R3. See, it is 6.41 volts, 8.41 volts. Okay, This is the readings for 15 volts. So V1 is 4.2, V2 is 2.53 and V3 is 4. Okay, so now the voltage across R1 is 4.2 and voltage across R2 is 2.53 and voltage across R3 is 8.41. If you add all the three, approximately you will get the supply voltage. Okay, next we'll just increase the voltage to the 20 volts. I'm just increasing the voltage. Applied voltage is 20 now. We'll see what is the voltage drop across each element. Okay, across R1 I'm measuring, it is 5.63. we'll write it here, 5.63 volts, and across R2 if you measure across R2, it is 3.37 volts, and across R3 it is, see, it is 11.2 volts. 11.2 volts. If you add all the three, approximately you will get 20 volts. Similarly, we'll go with the last one, or we'll do it again. 25 will add for 25 volts. I'll set the voltage source for 25. Okay, approximately 25 here. Now we'll see the voltage across R1 is, definitely it will be increases, because as you increase the voltage, it is 7 volts for 25 supply voltage. The voltage drop across R1 is 7 volts, and voltage drop across R2 is it is 4.19, so I can write 4.2 volts approximately. Okay, and voltage drop across R3 is how much? See, it is 14 volts. Okay, so 14.03, I can write it as 14 volts. So V1 is, across R1 is 7, across R2 is 4.2, and across R3 is 14 volts. Similarly, if I further increase this for 30 volts, that's the maximum voltage what we can apply from this regulated power supply. For 30, you can measure here, it is connected across R3, right? The voltage is 16.8 volts, and if I measure across R2, this is approximately, we get 5 volts. Okay, and across R1 it is 8.4 volts. You can observe here, as I increase the source voltage, okay, voltage drop across each element is increases. This is due to, because of increase in the current, because voltage drop is I into R. R we made it constant, we are not changing the values of R. As you increase the voltage, current increases, that will lead to the voltage drop is also increases. Okay, and in order to verify the Kirchhoff's voltage law, supply voltage will be equal to the sum of voltage drop across each element. Here voltage drop across V1, that is R1, V1, V2 and V3. Okay, so with this we can also do the theoretical calculations, and we can compare these theoretical calculations with the practical values in order to verify the Kirchhoff's voltage law. Thank you.